Hi, I'm Karen Stever with the Griffin GGS Pros. Thanks for joining me today for part 2 of Biostimulants. Today I'll be discussing silicon and phosphite. You can see the other episodes here, and I'd like to call your attention to part 6, where we're going to talk about which biostimulants can save you fertilizer, allowing you to reduce your fertilizer inputs. I want to spend just a minute on the sources of silicon. Silicon is the element, and it is taken up as silicic acid, a monomer molecule. Potassium silicate is much more available and economic than stabilized orthosilicic acid, and silicic acid has to be stabilized to remain as the monomer. It has to be manipulated somehow, otherwise it reverts to the natural tendency of silicon to form polymers. The potassium silicate is a polymer, but when it's in solution, it is in equilibrium with the monomer silicic acid, and that makes it a valid source for that monomer. A product that we commonly use is Agcel 16H. It's a water-soluble potassium silicate, and normal use rates are from 50 to 100 parts per million for that product. One of the effects of silicon is a reduction of insect feeding. Initially, it was thought that silicon just formed a mechanical barrier on the leaf surface or underneath the cuticle of the leaf. And now we know that induced systemic resistance is a part of the plant response to silicon as well that helps mitigate insect feeding. So in this diagram, we see the pathways that have been figured out that silicon works by. The silicon induces these systemic resistance. It can go by two pathways, and the interesting part is that the pathways are different depending on the type of insect feeding. So on the left of our diagram, we see that silicon will induce the production of enzymes that will stop the sap flow. So that's an antagonism to phloem feeders. And on the right side of this diagram, we see that the pathway is the jasmonic acid signaling pathway that signals the plants to produce volatile organic compounds that can either attract parasitoids, the enemies of the insects, or potentially make the plant less palatable to the insect pest. So these pathways are primed by the presence of silicon, by treatments with silicon, and definitely have an effect on the insect feeding behavior. Another effect of silicon is that it is good at reducing abiotic stresses on the plants. So here I'm going to go over an experiment that shows induced tolerance to cold temperatures. This is in corn seedlings, and on the very left we see a seedling that has been subjected to cold root temperatures after germination, and that plant is somewhat stunted. It was known for quite some time that you could add zinc and manganese to these to mitigate the effects of cold stunting in corn and other crops. But these researchers showed that silicon can also mitigate those effects, and we'll see why. So all of the plants were cold treated. This is the control. As we go across, we're adding increasing amounts of silicon. So initially at just 7 parts per million of silicon, we see a nice increase in plant growth, increasing as we go to 24. But when we hit 290 parts per million of silicon, we've started on the downhill side of that. If we look at the roots, we see much the same pattern. Someplace 7, 24, between 7 and here at 290 is going to be our sweet spot. And we talked about that being from 50 to 100 parts per million, which would be right in here. If we look at how silicon works, what they delineated was that it increases the production of a defensive enzyme, superoxide dismutase. Also increased in the plants were the production of antioxidants and defense molecules, proline and the phenolics. They also saw an increase in zinc and manganese that was translocated from the roots up to the shoots with the addition of silicon to these plants. And lastly, hormone growth levels were restored in the plants to normal levels, allowing that growth. Well, that's quite a few effects for one small molecule. So I've talked about just a couple, but this is the list of benefits that you can gain from silicon. It reduces water or increases the water use efficiency, reducing transpiration, wilting, and drought stress. It also protects against other abiotic stresses such as temperature, sun, heavy metal and salt toxicities. We saw how it can reduce insect and mite feeding. And silicon has also been shown to reduce the severity of some of these pretty serious diseases, at least in some crops. We saw in that example how it mitigated nutrient imbalances, helping to mobilize the zinc and the manganese up to the foliage of that plant. So silicon has a lot of effects, so many and so widespread that it has been proposed that silicon be classified as an essential nutrient. We also know that some plants can accumulate really high levels of silicon. That would be on those exterior surfaces as well as under the cuticle of the plant. But even without mass accumulation, plants are subject to the beneficial effects of the silicon. That's been recently shown. So I would recommend that you try this on your difficult crops, and especially try it in propagation where desiccation is a big issue and the silicon can mitigate much of that. One last note is that foliar sprays of silicon or products that are meant for foliar sprays only form the physical barrier, so they can help with this disease or insect intrusion, but they won't induce the systemic resistance that we can get from a drench application. So next we're going to talk about phosphite. Phosphite's been known as a fungicide for a long time. It is not a nutrient. The difference between phosphate, PO4, and phosphite shown here is the number of oxygens shown in red in our little diagram. In phosphite, one of those oxygens is replaced by a hydrogen, which is not shown in the diagram. So chemically, these two molecules act very differently. However, the phosphite can eventually be converted by soil bacteria into phosphate, but still it's not a nutrient. That is not usually relevant in the overall nutrition of the plant. The other feature of phosphite is that it's unique among all fungicides in that it will migrate down from the foliage down to the roots, and so you can get some protection against root diseases from a foliar application. However, to get the full biostimulant effect, a drench or soil application is still recommended. So here is an example of a grower trial. On the left of each photo, we have an untreated plant, and on the right, a plant that's been treated with phosphite and then photographed 4 days later. And what we see in the root zone is that we have increased branching of the roots already showing up after 4 days. So that plant's building a stronger root structure. And in the top, in this 4 days, we see just a little bit of growth stimulation as well. So we've known for a long time that phosphite is a really good preventative fungicide for Pythium, Phytophthora, downy mildew, and for some leaf spots. So it also is unique as a fungicide in that it translocates from the foliage down to the roots. There's no other fungicide that does that. So if the fungicidal properties aren't enough to do it, this root stimulation may get you to want to try the phosphite. How the phosphite works is it actually stimulates the production of an IAA precursor, IAA being a rooting hormone. Another noted effect of the phosphites in food crops is an increased yield, increased firmness, and increased sugar content of the fruits. The two biostimulants I discussed today, silicon and phosphite, are both relatively cheap and easy to add into your production. The rates are pretty well defined, and on top of that, the effects are well defined as well compared to some of the other biostimulants. So this might be an easy entry point where you would like to give them a try. I hope you'll join us for the other episodes of this biostimulant series.